Hi everyone, this is Dr. Saeeda Falafini from Cal Poly Pomona. In this video, we are going to look at queuing systems that have more than one servers. In the previous session, we talked about MM1 discipline for the queuing, C Infinity. That was the system we talked about. That was section 20.5 of the textbook. Section before that we looked at was MM1. GD infinity, and that was section 20.4 of the textbook. So that was the first queuing system we looked at, and was the second queuing system we looked at. Can you tell me what was the difference between the first and the second one?
The first one had unlimited capacity in the system, and then the second one, there's a limit capacity for the system.
Exactly. There is a limited capacity in the system, in the second one, but the first one has unlimited capacity. Then we go to the third queuing system, which is MMS, GD, infinity, and infinity. And in this system, we, instead of just one server, which was the case for the first queuing system, we had one server. And for the second queuing system, also we had one server. But in this system, we are going to have S parallel servers. For example, 2, 3, 10, or whatever number there may be. We have S parallel servers that are working in the system. And this is going to be section 20.6 of the textbook. So we are going to look at the MMS system. So, and as I said, this is the system in which the number of servers in the system is S. Every system we looked at so far, the customers arrive to the system and there is one server that is providing service. The system either had limited capacity or not. However, here we have more than one server, and this S shows the number of servers that are working in parallel, not in series. So these servers are working in parallel. So for example, if I have 3 servers, I have 3 servers here that are working in parallel. When the customers come and they are waiting in the queue, then they can go to any one of these servers that are idle, and then they can leave the system. They don't need to go through all these 3. They can go through any one of them. For example, if they may go through the first server and then they leave the system, exit. They may go through the second server and then they leave the system, or the third server and then they leave the system. So here I can have from 1 all the way to S number of servers in this system. So that's the meaning of MMS. So here, when I talk about the system, basically this is what I mean. This is the border of the system. Okay, the rate of arrival to the system is still lambda. The customers arrive to the system with the rate of lambda. However, the rate of service of each one of the servers is mu. Okay, so each one of the servers can process the customers with the rate of mu per hour or per unit of time, whatever it is. Okay, so what we need to also calculate is the rate of exit from the system. So this is rate of exit from the system. And again, in everything we have looked at so far, always the mu was the rate of exit from the system, because we had only one server. So the rate of exit from the server was equal to the rate of exit from the system, because there was just one server in the system. But here, since there is more than one server, if we have the rate of exit of each server, still we have to calculate the rate of exit from the system as well. Okay. Now, in this system, what are the possible values for number of customers in the system?
0, 1, 2, 2, j minus 1, j plus 1.
Can I go above that?
It's a really big number. Infinity?
Yeah, I can go up to infinity. there's no limit on the capacity of the system, right? So the number of customers in the system can go up to infinity. If all the servers are full, they are just going to stay in the line, and that's perfectly fine. But the number of customers in the system can potentially go to infinity. And we assume that the rate of arrival of customers to the system doesn't depend on how many customers are in the system. So the rate of arrival, no matter how many customers are in the system, is going to be lambda. Okay. This is the assumption that we had in previous two systems as well. So the rate of arrival does not depend on how many customers are in the system. It's generally lambda. However, what is the rate of departure? So if there is one, if the state of the system is 1, which means there is one customer in the system, where is that customer?
He's at a server.
In any one of the servers. And in that scenario, what is the rate of exit from the system? That would be the rate of the exit from this one machine, right? So from this one machine, the customer leave the system with the rate of, would leave the machine with the rate of mu. So the rate of exit from the system would also be mu. What if there are two, system is in state 2, which means there are two customers in the system. If there are two customers in the system, then both of these customers will go get the service, right? They don't wait in the line if the servers are idle. So they get the service, and each one of the machines provides service with the rate of lambda with the rate of mu per hour. So the rate of the exit from the system will be 2 mu 10, right? This is the example that I think previously I told you guys as well. So let's assume there are two machines working here. The first machine can provide service to 10, let's say, customer per hour. The second machine can also provide service to 10 customer per hour, right? So then the rate of exit from the system will be 20 customer per hour. Each one of the servers can provide service to 10 customer per hour, so the rate of exit from the system will be 20 customer per hour. That's why here I also added the rate of service or the rate of departure from the first machine and the second machine, and thus the rate of exit from the system will be 2 mu. Okay, so that's where this comes from. And I want you guys to please make one little change. In this J things, put S instead of J. It doesn't matter much, but S plus 1. Okay. Okay. So S minus 1, S plus 1, and then goes into infinity. Okay, so this goes all the way. So let's assume there are 3 customers in the system. So then all 3 servers are busy. What is the rate of exit from the system then?
3 mu.
3 mu, okay? And let's go all the way to S. So let's just go all the way to S minus 1. Let's assume this is machine S minus 1. There are S minus 1 customers in the system. So all these S minus 1 servers are busy. What is the rate of exit from the system?
30.
Where do you get 30?
S minus 1 mu.
S minus.
That would be 3 stations are filled.
No, I didn't say 3. I said, so this is general scenario. I assume I have S servers, right? And now I say, let's assume all the servers there are S minus 1 customers in the system. So S minus 1 of these servers are busy. So only one of them is idle, and S minus 1 of them are busy. Each one of them has the rate of exit of mu. So the rate of exit from the system is S minus 1 multiplied by mu, right?
Yes, yes.
Okay. Now let's assume there are S people in the system, or S customers in the system. Obviously, all these servers are going to be full. What is the rate of exit from the system?
S times mu.
S mu. And now let's assume there are S plus 1 customer in the system. What is the rate of exit then?
S plus 1 mu.
Okay, tell me, Renee, if there are S plus 1 customers in the system, what happens to these customers? How many of them go to the servers? There are S servers. How many of them go to the servers?
If there's S plus 1 customers,
There are S plus 1 customers in the system. How many of them will go to the servers immediately?
all of them.
There are S servers. How all of them?
If there are S servers, but there's S plus 1 customers, J would go, but the plus 1 will wait in queue.
S of them will go to the servers. All the servers will be full, and just one of them will stay in the queue, right? There are S servers. So if I have S plus 1 customers in the system, all the servers will be busy. S of them will go to the servers, and the last one will just wait in the line. What if I have S plus 2 customers in the system?
Your queue goes to 2.
Yeah, S of them go to the servers, and 2 of them wait in the queue. So no matter if there is S plus 1 people in the system, or S plus 2, or S plus 3, and so forth, all the servers are busy, right? And the rest are waiting in the queue. In that scenario, what is the rate of exit from the system?
S mu.
S mu, because all the servers are busy. S servers are busy. Each one of them has the rate of exit of mu. So the rate of exit from the system is S mu. So even if so obviously we just, saw that if there are S people in the system, all the servers are busy, and the rate of exit from the system is S mu. But we just saw that even if there is S plus 1 people in the system, still the rate of the exit will be S mu. If there is S plus 2 people in the system, still the rate of the exit is S mu, and so forth, all the way to infinity. So if there is more than S customers in the system, all the servers will be busy, the rest of the people will wait in the line, and the rate of exit from the system will be S mu. Okay? So that's basically how things work in this type of system. So for this system with S servers, we can say that if J, which is number of customers in the system, is less than or equal to S, which is number of servers, we can say that all customers are with servers. Okay, if the number of customers in the system, J, that's always that's the notation we always use. J, number of customers in the system, is less than or equal to number of servers, then all the customers in the system are with servers. This is also, if I wanna ask you a question, I also may ask you what percentage of the time there is no customer in the line. If I ask you that question, then this is the answer to that question as well. You have to find the percentage of the time that the number of customers in the system is less than number of servers. That percentage of the time, every customer that is in the system goes right away to servers. And as a result, there is no customer in the line. Okay, or again, in this scenario, all the customers are with the servers. And the other scenario is that if J greater than S, that's the scenario where I can say that all all servers are busy. I can say then equal j greater than or equal to s. I can say that's the scenario when all servers are busy. So if I ask you what percentage of the time all servers are busy, you have to find the probability of the probability that the number of customers in the system is greater than or equal to s. That probability or that percentage of the time gives me the percentage of the time where all the servers are busy. Okay. So there is nothing tricky here. These are just common sense, right? I just want to mention that so you don't get confused. If I ask a question, what percentage of the time there is no customer in the line, there is no tricky thing about it. So you just have to find this probability and that's it. And we'll learn how to do it in a second. Okay. Now, in this system, what are the formulas in this system? In this system, first of all, rho equals to lambda over S mu. And I still want rho to be less than 1 and greater than or equal to 0. So I want this to hold. Pi j is calculated as S rho to the power of j pi 0 divided by j factorial. This is for j, number of people in the system, from 1 all the way to s. And pi j, if j goes above s, to infinity, pi j is calculated using this formula. Okay, so the formula for pi j in this system is one of these. For example, let's assume I'm looking at MM10 system. What does that mean? How many parallel servers are in this system?
10.
10 of them. Okay, so now let's assume I asked you calculate pi 2. What does pi 2 means? Probability that?
Probability that there's 2 customers being served,
There are 2 customers in the system.
or just in the system? Okay.
Okay, so I calculate, so the system is MM10 and I can ask you to calculate pi 2. Which one of these formulas you have to choose? The first one or the second one?
The first one.
The first one, because this is for j from, in this example, from 1 all the way to 10. So if I ask you to calculate pi 2, you have to pick the first formula. If I ask you to calculate pi 15, what does this mean? The probability of
15 people in the system.
having 15 customers in the system. And for this one, you have to definitely use the second formula, because the second formula is for s from 10 all the way to infinity. So for pi 15, you have to pick the second formula. For pi 2, pi 7 all the way to pi 10, use the first formula. And as you can see, for pi 10, it doesn't matter to use the first formula or the second formula. They both return the same results. But anything less than 10, first formula. Anything above 10, the second formula. So that's the formula for pi j. So when you take note, make sure to write this clearly so that you know which one to pick depending on the question I ask. And then, and as you can see here, this formula for pi j depends obviously on pi 0. Rho is, you know, right? Rho, we know lambda, we know mu, we know s. Rho is something we know. The only thing that you need to know in this formula to be able to calculate pi j is pi 0. I haven't told you how to calculate pi 0 yet. Just keep that in mind. The other thing here is that if I ask you probability of all servers busy, can you tell me one more time what is this probability that all servers are busy? That's probability of J, which means number of customers in the system to be. What is the relation between J and S? Number of people in the system should be
Greater.
Greater or equal to?
greater than or equal to S. Okay, that's when the number of people in the system is greater than or equal to S. That's where all the servers are busy. That equals to S rho S pi 0 S factorial 1 minus rho. This, you can also write this in, if I want to just as 1 minus probability of at least one server is idle. Okay, right? So probability of at least one server being idle means that there is definitely less than S customers in the system. And if there is less than S customers in the system, then not all the servers are busy. So just keep these things in mind. So if I ask you, what is the probability that all servers are busy? So those are the questions I asked you. You know how you have to calculate. You have to know that this is what you need to calculate. I may ask you, what is the probability of that at least one server is idle? If at least one server is idle means probability of J, which is number of customers in the system, being less than S. And if you need to calculate probability of S less than S, that is 1 minus probability of J greater than or equal to S. Okay, so just, and again, there's nothing tricky about this. These are intuitive. When you think about them a little, you will see how intuitively all of this makes sense. But just know them and make sure they are clear for you so that if I ask these questions in the exam, you know exactly what you need to calculate. And then, and again, one more thing I want you guys to pay attention to is that, again, here also, this formula depends on pi 0, and we still don't know how to calculate pi 0. S we know, rho we know, everything we know other than pi 0. Pi j also depends on the pi 0 here and here, and so we need to be able to calculate pi 0 to be able to answer any questions so far. And the other thing is LQ. LQ is probability of J greater than or equal to S, rho 1 minus rho, and WQ equals to probability of J greater than or equal to S, S mu minus lambda. Okay, so this tells us average number of people in the queue, average time waiting in the queue, right? WQ average time waiting in the queue, LQ average number of people in waiting in the queue. Average number of people who are standing in the queue. WQ is average time waiting in the queue. So for these ones also you need to be able to calculate probability of J greater than or equal to S to be able to answer WQ and LQ. Probability of J greater than or equal to S is something that we can calculate from this formula. And to be able to calculate this formula, we also need pi 0. Okay. And LS, we know that equals to lambda WS. and WS is the time spent in the service, right? The time spent in the service, we know that is always 1 over service rate. So LS equals to lambda over mu. That one is easy. And then if I want to calculate L, number of people in the system, equals to number of people in the queue plus number of people in the server. That's going to be probability of J greater than or equal to S rho 1 minus rho plus lambda over mu. And then W, the time waiting in the system, is the time waiting in the queue plus the time spent in the servers. And we know WQ, we know WS, so you can just put them in this formula. So here is the formula for WQ, and the formula for WS is 1 over mu, so we can just put them in this formula and find W as well. But also pay attention that to be able to calculate L and W, I need to be able to calculate this probability. And to be able to calculate this probability, I need to be able to know pi 0 from here. So then basically pi 0 is the main thing that I need. Okay, so let's see how this is going to happen. So far, just make sure to know the formulas. So put a square around them for L for LWQ, LSWS, LQWQ. So make sure you write down the formula for each one of these clearly, for each one of these and so forth. Okay, now. So just in the top, I wrote the formula for probability of J greater than or equal to S, right? That's the probability of all the servers being busy. And I said that that's equal to this value. Okay, that's what I just wrote here. So I just rewrote this formula again. Yeah. So that's the formula. In your textbook, these probabilities of probability of J greater than or equal to S have been calculated for you actually. If you know S, which is number of servers in the system, and if you know rho, which is lambda over S mu, these probabilities have been calculated for the system that you are dealing with. And this is in, and these are in page 1088 of your textbook, right? You can see my book, right? My screen. So in the page 1088 of your textbook, there is a table called table 6, which calculates probability of J greater than or equal S for you for MMS systems, the system that have S parallel servers. If we know the number of parallel servers in this table, it goes all the way to 7, okay? If we don't know the number of parallel servers, and if we know the value of rho lambda over S mu, which goes all the way from 0.1 to 0.95, then the values, the numbers inside the table are actually the probability of J greater than or equal to S. So for example, if I tell you that a server has, I'm looking at the system MM3, so the server has 3 servers, the system has 3 servers, and I do my calculations and I find out lambda, which is, rho, which is lambda over S mu, is 0.7 in this system. Then probability of J greater than or equal to S in this system for 3 servers and for rho equals to 0.7, that probability of j greater than or equal to s or greater than or equal to 3 is 0.51. Okay, so
are you trying to show us your board, or are you still on the book?
You don't see my screen?
We can only see the book right now, like table 6.
Yeah, the table 6. That's what I'm showing right now.
Okay, my apologies.
No worries. Yeah, so here, so for that system, if I tell you I'm looking at the MM3 system, so S equals to 3, number of servers is 3. And if I have calculated rho lambda equals to S mu, and let's assume it has ended up to be 0.7, then probability of J greater than or equal to 3 in that system is going to be 0.51. So you can calculate, you can get that probability from this table. And if you can get that probability from this table, which again is on page 1088 from your textbook, if you don't have the book, you can just take a picture from this screen right now, because that's the table that we are going to use for your homework and in the exam as well. So you can just take a picture from this screen. I'm going to switch back to my iPad. Okay. So if this probability, if this value we can get that from table 6. So this comes from table 6. Then I can use this formula and I can find pi 0, because then the only unknown here is pi 0. This comes from table 6, S and rho, I know them. Then I can calculate pi 0 from this formula. So then pi 0 is going to be probability of j greater than or equal to s factorial 1 minus rho okay, so that's going to be pi 0 here. And this is important to know this one. Once you get probability of j greater than or equal to s from the table, you calculate pi 0, and once you calculate pi 0, you can calculate pi j's, and basically you can calculate anything else. Here also you need pi 0 to be able to answer these questions and everything else. So if you can calculate this probability from the table and pi 0, then you can answer any question, because in all these formulas, we either need pi 0 or I need probability of j greater than or equal to s. So you're all set then. So basically this is the main thing to know: how to get pi 0, how to get this number from the table, how to get pi 0, and then everything else is just based on the formula.